Can every question be settled by a procedure? In the early 20th century, mathematical logic faced that question with unusual urgency. David Hilbert's decision problem asked whether there could be a general, effective method for deciding the formulas. Not every truth in every field, not every question a human being can ask. A precise question about what rules can guarantee. In 1936, Alan Turing helped provide a decisive answer. He described what a rule-governed calculation is and showed that there are boundaries such a calculation cannot cross. That double achievement matters. The universal machine opened a path toward general-purpose computing. The limits of computation warned that no procedure can settle everything. Before electronic computers, the word computer could describe a person performing calculations by rule. Turing began with that human activity. Imagine a worker following exact instructions with paper, pencil, patience, and no need for intuition at each step. An effective procedure is finite, explicit, and repeatable. It tells the worker what to inspect, what to write, and what to do next. Turing's insight was to turn that familiar activity into a precise mathematical model. By doing so, he gave logicians a way to distinguish between tasks that can be completed by systematic rules and tasks for which no such general rule exists. The result was not a rejection of mathematics. It was a more exact account of its reach. Turing's machine was an idealized device, not a blueprint for a desktop computer. It had an unbounded tape divided into cells. A head could read a symbol, write a symbol, and move one cell left or right. The machine also had a finite set of internal states and a table of instructions. If it was in one state and encountered one symbol, the table determined the next small action. Read, write, move, change state, then repeat. The elegance lies in the simplicity. From these elementary operations, one can describe extraordinarily complex procedures. But simplicity is not omnipotence. The machine can carry out a method only when that method can be expressed as effective rules. Then came the leap that gave the episode its name. Turing realized that the description of a machine's instructions could itself be encoded as symbols. A universal machine could read that description from its tape and emulate the specified machine's behavior. In modern language, instructions and data could be represented in the same symbolic medium. This did not create software in the everyday sense, and it did not make a physical computer appear in 1936. But it revealed a principle that would become central to general-purpose digital computing. One machine can perform many different tasks when it is given different encoded instructions. A machine need not be built anew for every procedure. The most important word in this story may be limits. Turing's model did not show that a machine can solve every conceivable mathematical problem. It made possible a rigorous demonstration that some tasks are not computable by any general algorithm. Alongside Alonzo Church's independent work, Turing's result showed that the full decision problem for the functional calculus has no solution of the hoped-for kind. Some questions can be formalized, calculated, and checked. Others resist any universal decision procedure. This is not a failure of machines. It is a fact about formal systems. The universal machine is powerful because it makes the scope of computation clear. It is profound because it makes the boundary clear too. During the Second World War, Turing brought his mathematical skill to Bletchley Park, Britain's code-breaking center. He was a leading cryptanalyst in Hut 8, which worked on German naval enigma. The achievement was collective. Polish cryptanalysts had made crucial pre-war breakthroughs. Turing, Gordon Welchman, and many colleagues contributed to the British bomb and to the relentless work of interpreting intercepted traffic. No single person broke Enigma. Yet Turing's contribution was major. The war showed that abstract reasoning, mechanical assistance, and human collaboration could be joined in urgent practical work. It also showed how much depends on the institutions and people around a technical system. After the war, Turing worked at the National Physical Laboratory on the automatic computing engine, a detailed stored program computer design. Later, at Manchester, he worked in the world of early electronic computing. The theory of the universal machine had not simply turned itself into hardware. Engineers, mathematicians, technicians, institutions, budgets, materials, and teams had to make new machines real. In 1950, Turing posed another famous question in his paper Computing Machinery and Intelligence. Can machines think? Rather than begin with a definition of thought, he proposed an imitation game based on typed conversation. His move was provocative. He shifted attention from hidden essence toward observable performance. The imitation game is often reduced to a simple slogan. If a machine can fool a person in conversation, it is intelligent. Turing's actual proposal is more interesting than the slogan. It is a behavioral experiment designed to make a difficult question discussable. It does not settle whether a system is conscious. It does not prove that fluent language equals understanding. And it is not a single standardized examination that modern systems continuously pass. Today's language models can produce strikingly convincing dialogue. That fact deserves attention, but it should lead to sharper questions. What can a system do? Where does it fail? What evidence supports the claim? And what consequences follow when people rely on it? In 1952, Turing moved into mathematical biology with the chemical basis of morphogenesis. He proposed a possible mechanism through which interacting chemicals, reacting and diffusing through tissue, could generate patterns from an initially near homogeneous condition. The paper explored idealized systems and suggested links to phenomena such as dappling, phyllotaxis, and gastrulation. It did not prove that every stripe, spot, leaf, or living form has been explained, nor did it reduce life to an algorithm. Its deeper lesson was subtler. Simple local interactions can sometimes give rise to complex visible order. That insight continues to shape mathematical biology, chemistry, and the study of pattern formation. Turing's life also reveals a different kind of limit, the cruelty of institutions that decide which people may live openly. In 1952, he was prosecuted for indecency because of a relationship with another man. He pleaded guilty for indecency because of a relationship with another man. He pleaded guilty and chose probation, conditional on hormonal treatment intended to reduce libido, rather than imprisonment. The prosecution was not a technical problem or a consequence of his theory. It was discrimination, enforced through law and social prejudice. Turing died in 1954 at the age of 41. This history should not be turned into a melodramatic image of a machine destroying its creator. It is the record of a person and a society that failed him. The universal machine helped establish a logical principle. Post-war computer architecture made that principle practical in several places at once. John von Neumann's 1945 EDVAC report and the Institute for Advanced Study Computer helped standardize an influential arrangement in which programs and data could share a common memory. But the history was collaborative. Engineers and mathematicians at the Moore School, at Manchester, at the National Physical Laboratory, and elsewhere developed different machines and methods. No single person converted Turing's paper directly into the silicon processors of today. The path from theory to hardware ran through many materials, many institutions, and many decisions. Turing's universal machine did not make the mind weightless. It clarified a relation between symbols, rules, and machines. It showed how powerful a general-purpose procedure can be, and why even such a procedure has limits. His wartime work showed that technical achievement is collaborative. His later work on intelligence and biological pattern turned calculation toward new questions without settling them once and for all. And his persecution reminds us that societies can fail the people whose talents they celebrate. The universal machine belongs to the history of computation. The responsibility for what is computed, built, governed, and valued still belongs to us.